So in this video, we will analyze the acceleration time graph. Let's do it. So here we have some randomly chosen intervals and the accelerations given as such. Notice I don't have any curved lines here. I could, but as we'll see, that actually corresponds to very complex motion. Well, let's just stick with the basics. When we read the graph, what information is given? Acceleration. Now, if we consider the slope of an acceleration graph is delta A over delta T. So consider the units. This unit divided by this unit. Well, the unit in the vertical is meters per second per second. So meters per second divided by seconds. So if you carefully do the algebra on this, though it looks like things should cancel here, they don't, as you probably know. We actually get meters per second cubed. So the slope is meters per second cubed. What physical quantity does that correspond to? Meters per second per second per second. The rate of change of slope, well, of a velocity graph. That'd be right, wouldn't it? The rate at which the slope of a velocity graph changes. Or the time rate of change of the time rate of change of the time rate of change of position. But we don't have to get so confusing with that. We have an acceleration and it's changing. If the acceleration changes, there is an engineering term that's associated with that happening, and it's called the jerk. Don't get any ideas now. Well, what is the area? Let's consider the area. Consider a couple sections here. We're always thinking about between the plot and the zero axis. So here's a couple cases in point. Consider the units. The vertical, meters over seconds squared, times the horizontal, seconds. One of those seconds go away, and we get meters per second. So we have three possibilities. What's meters per second? It's a motion term, unit I should say. So this must correspond to speed, velocity. There's actually another possibility, and it's change in velocity. And it actually is delta V. How much the velocity has changed. If you want to get the velocity, you need to know something about the initial. What was it doing? So V, the final velocity, is initial plus the area, which could also be said initial plus delta V. Well, delta V is V minus V0. So V plus V minus V0 is V. That's not V factorial. It's just that I'm excited when something like velocity turns out to be velocity. Woohoo! Now, how should you think about the acceleration plot? To get information about the motion after answering the two questions, namely, okay, I'm looking at an acceleration graph, and what information, question 2, can I get from these three ideas? We've just done that. Well, we're interested in deducing the velocity and the position graphs from the acceleration graph. We're going to do that. So first of all, slope, and the other two examples, position graph and velocity graph, we said the next one, for velocity graph, or the slope of a position graph is velocity. Slope of a velocity graph is acceleration. Now slope of an acceleration graph is jerk. But that's kind of neat. But generally, we don't even have to consider a changing acceleration. So it's usually 0 for the kind of problems that we work with. Now, in the real world, changing accelerations are very common. Anytime you crash into something, anytime you push off the floor and you're walking, you are having some continuous jerking going on. I didn't call you a jerk. I just said you are jerking. Okay. Now, is the slope increasing or decreasing in value? Well, you can analyze that, but I'm going to just say seldom. That usually is not something we have to worry about. Usually what we have to worry about is the acceleration plus or is it minus, positive or negative. So that question gives the sign of the slope on the velocity time graph. So let's consider that for a moment. So just clarifying again that we're really not interested in plotting the jerk graph. We really want to get velocity and position from acceleration. So here's our acceleration plot. We have positive acceleration, negative acceleration. What about this? This is negative over the entire interval. So that's an acceleration that's negative, but increasing, getting more positive or less negative, same thing, and then 0. So we're going to, at the same intervals of time, for each of these segments, we're going to plot the velocity, then we'll do the position. So, first of all, we recognize that the value of the acceleration is the slope on the velocity graph. So since this is constant, it means the slope is constant and it equals this value right here. So that's a straight line segment. Now, a couple notes over in this area. You must be given the initial velocity to know where to start, otherwise assume it's 0. Well, I'm going to give it an initial velocity that's non-zero, right about here. Okay. If that's not given, you have no idea. You have to assume that v0 is actually 0. Is the acceleration plus or minus, or is it 0? Well, it's plus in this case, and that gives the slant on the velocity time graph, the nature of the slope. So the velocity is going up, and it's equal to this value. The velocity is increasing in value along here, but it's at a constant rate, giving us a constant acceleration. The next segment, the velocity is going down because the acceleration is negative, and the slope of the velocity graph gives us this value. There it is. Notice it's a lot less steep, but it's negative. And what about here? Here, the acceleration is getting increasingly positive. So the acceleration, though, is negative, which means the velocity is going down. And at the end of the interval, the acceleration goes to 0. So at the end of this interval, the velocity is going toward a constant value. So what I mean by this somewhat strange symbology here is the velocity is decreasing until it becomes constant. So how am I going to show that? Well, it isn't going to look that amazing, really. It's just this. Wow. Okay, so I have a value of slope here. Negative is equal to this value. Let's go about halfway through. This thing is curving upward a little bit, so at the middle point it's less steep, corresponding to this negative value. And at the end, I level out so that the slope is 0, corresponding to the acceleration. So that's it, just that little bit. Don't get carried away thinking there has to be some drastic visual change in the graph. There doesn't. It's not a big change. And then this last segment, no acceleration, the velocity stays constant, just like this. I put this note in here that this velocity graph is curved. And seldom. That is actually very complex, unless you have the mathematical equation that describes that motion particularly. And then calculus will handle it real easily. But for first year physics, we're generally assuming that we have changing velocities that are changing uniformly, constant acceleration. Last thing, map it to a position graph. Now, to plot position, we must be given the initial to know where to start, otherwise assume it's at the origin. That we're starting at 0. And is the velocity constant, increasing, or decreasing? Which will, since the slope of this graph is the velocity, the way this question is asked, the answer to the questions will tell you what happens to the slope on the x versus t graph. So in the first case, we have positive acceleration. The slope of this plot equals these values. The values are getting bigger. So the slope is getting larger. To do that, we have to show the slope getting larger, which it is here. Also in here is the fact that the slope at the beginning is not 0, it's V0. So you see this thing? It doesn't start horizontal, it starts at an angle. The slope of the beginning point is this value. And then it increases uniformly to this value at the end of the interval. In the next one, we still have positive velocity, but that velocity is getting less and less. So this slope is positive over the whole interval, but at the end of the interval, the value of the slope on the position graph will be this value, not this value. Interesting. It's negative acceleration, isn't it? There it is. It's a upside down bowl kind of thing. It's curvy downy. This first part was curvy uppy. It transitioned to curvy downy. That's a nice way you can think about it. Very technically pleasing as well. Haha. So, again, notice, not much difference. It almost looks like a straight line, but it's curved to correspond to these different values here and here. Then we continue to have negative acceleration. That negative acceleration is changing. The velocity is approaching a constant value, but the velocity is constant the whole time. So the slope value here, did I say the velocity? The velocity is positive the whole time. Not sure what I said. But getting a slightly less positive. At the end of this interval, the slope of this line better equal this value. At the beginning of the interval, the slope equals this value. Very small change. So really what's happening is this is curving, and it's curving at a changing rate, which we don't have to worry about understanding the details of or visually showing it correctly. But I kind of try to show this curving a little bit more here and then almost leveling out. At the end of the interval, the velocity is arriving at a constant value, meaning the slope is constant, meaning it's a straight line. It's got a positive slope. So at the last segment, velocity being constant, notice the slope of this is this value, this constant value. Notice the progression from simplicity in the graphing, the plot itself, to more complex, even more complex. This is a very complex plot, but the physical quantity position is a simple idea, just where am I? But where I am changes in a fairly complex way. So the plot is complex. There's something else you want to notice, and it's kind of a rule of thumb. So on the position graph, if you don't smoothly connect all the line segments, you've done something wrong. You don't have any sharp corners like you can have on a velocity graph. And you certainly don't have any discontinuities like we show here. A position graph is always smoothly connected, so the curves don't have any corners or discontinuities. So that's one way to give yourself a check to make sure that it passes the reasonability test. If you show anything other than that, you've got something wrong. Okay? So now we're going to need to practice these concepts, and we'll do that next.